there is a moment, and if you can picture it clearly, everything that follows will hit you differently, when you are no longer sure which direction is forward. You are falling. Not downward, not toward anything you recognize as ground. The stars around you have stopped looking like stars. They have bent, curved, smeared themselves into arcs, stretched into rings of impossible light that circle something in front of you, something that looks like a perfectly round window cut into the fabric of space itself. Through that window you can see another sky, different constellations, a different arrangement of galaxies, ancient light from a place that may be billions of light-years away, or perhaps just across the room in some higher dimension you have no word for. And you are moving toward it, faster now. The rings of light are tightening. The window is growing. And in approximately the time it takes your heart to beat twice, you are going to cross the threshold. This is not a metaphor. This is not a science fiction premise stripped of rigor. This is what the mathematics of general relativity actually predicts, what the physics genuinely allows, and what an accurate three-dimensional simulation of a traversable wormhole actually shows when you render it properly. Scientists have done exactly that, rendered it. Teams at NASA's Goddard Space Flight Center, theoretical physicists working with Kip Thorne at Caltech, researchers at multiple universities around the world have taken Einstein's field equations, run them through ray tracing algorithms that simulate how light actually bends in extreme curvature, and produced images. What those images show is not what Hollywood imagines. It is simultaneously more strange, more beautiful, and more terrifying than anything a production designer has put on screen. So let's do this properly. Let's fall through a wormhole together, step by step, moment by moment, and let's be completely honest about what physics says you would actually experience. Not the sanitized version, the real one. But first, let's establish something that trips people up immediately. The word wormhole makes most people picture a tunnel, a tube, a passage you enter on one end and exit from the other, like a highway underpass. Throw that picture away. It is completely wrong, and it will make everything harder to understand. A wormhole is not a tunnel through space. It is a fold in spacetime. Imagine you are an ant living on the surface of a flat sheet of paper. You want to cross from one side to the other. The long way around is to walk the entire length of the paper. But someone could fold that paper so the two sides touch, and you could step through a tiny hole from one face to the other in a single stride. The paper did not become shorter. Space itself did not shrink. What happened is that the geometry of the surface changed. 2 points that were far apart in flat geometry became adjacent in folded geometry. A wormhole is exactly that fold, but in 4-dimensional spacetime, not 2-dimensional paper. The mathematics behind this was not invented by science fiction writers. It was published in 1935 by Albert Einstein and his colleague Nathan Rosen in a paper titled The Particle Problem in the General Theory of Relativity. They were not trying to build a cosmic transportation network. They were trying to solve a completely different problem, whether fundamental particles like electrons might be described as topological features of space-time itself, rather than as separate objects sitting in space. In the process, they derived what they called a bridge connecting two separate sheets of space-time. The solution emerged directly from the Schwarzschild metric, the mathematical description of space-time curvature around a spherically symmetric mass, extended to its maximum possible range. Einstein and Rosen found that at the mathematical heart of what we now call a black hole, the geometry does not simply terminate. It connects. It bridges to another region of space-time. For 20 years, almost nobody paid serious attention to the Einstein-Rosen bridge beyond academic curiosity. It was a mathematical artifact, an elegant eccentricity in the equations. Then, in 1957, a physicist named John Archibald Wheeler arrived at Princeton. Wheeler was one of the most imaginative theoretical physicists of the 20th century, the man who later coined the term black hole at a conference in 1967, the man who worked with Niels Bohr on the theory of nuclear fission, the man who described the universe as a participatory system in which observation itself shapes reality. Wheeler looked at Einstein-Rosen bridges and saw something more. He named them wormholes, and he began asking a question that nobody had seriously posed before. Could you actually travel through one? The answer that came back from the mathematics was brutal. No, at least not through the kind that Einstein and Rosen had found. Here is why. And this is the first drop on our roller coaster of physics, the first moment where the ground falls away beneath you. A Schwarzschild wormhole, the natural kind that emerges from the mathematics of a non-rotating, uncharged black hole, is not static. It is dynamic, and its dynamics are catastrophic for any would-be traveller. The wormhole throat, the narrowest point of the connection, forms, pinches off, and collapses back to zero size in a length of time so short it makes human comprehension struggle. For a wormhole with the mass of our Sun, the throat exists for approximately 10 microseconds before it collapses. 10 microseconds. For a wormhole with the mass of the Earth, we are talking about fractions of a nanosecond. Nothing, not even light, can traverse the throat before it collapses, because the collapse happens at a rate faster than anything can cross it. The wormhole is, in a very specific technical sense, non-traversable. You cannot get through. The universe, it seems, is protecting its topology. But then, and here is the first surge back up the track, the moment the physics throws you forward again. In 1988, two physicists at Caltech made a discovery that changed everything. Their names were Michael Morris and Kip Thorne. Thorne, who would later win the Nobel Prize in Physics in 2017 for his role in detecting gravitational waves, was inspired by a very unusual source, a phone call from Carl Sagan. Sagan was writing his novel Contact, and he wanted to use a wormhole as the mechanism by which his protagonist travels to the star Vega. He asked Thorne, "Is there any way to make a wormhole work? Is there any configuration of space-time curvature that would allow traversal without the throat collapsing?" Thorne and Morris set out to answer the question properly. Instead of starting with a black hole and asking what it produces, which gives you the Schwarzschild solution and the collapsing throat, they started from the other end. They asked, what kind of space-time geometry would allow a stable, traversable wormhole to exist? They specified the properties it would need: a throat that does not collapse, tidal forces that would not kill a human traveller, a traversal time measured in hours or days rather than nanoseconds. Then they worked backward through Einstein's field equations to find out what kind of energy and matter would be needed to produce that geometry. The equations gave them an answer. A traversable wormhole is possible. It is mathematically consistent with general relativity. But it requires something deeply strange, something that does not exist in the everyday world, something that may or may not exist at all. The throat of a traversable wormhole must be threaded with matter that has negative energy density. Not just low energy, negative energy. Matter or a field that pushes spacetime outward rather than inward, that has a gravitational effect opposite to ordinary mass. Morris and Thorne called it exotic matter. Without it, gravity would immediately cause the throat to collapse, just as in the Schwarzschild case. With it, with enough of it, configured correctly, the throat could be held open, stabilized, made passable. Most physicists, when they first encounter this requirement, assume the problem is solved. Negative energy doesn't exist. End of story. Go home. But here is where the physics gets genuinely vertiginous, genuinely strange, in a way that should make every person on Earth feel something deep about the nature of reality. Negative energy does exist. We have measured it. We have created it in the laboratory. The phenomenon is called the Casimir effect, and it was predicted by the Dutch physicist Hendrik Casimir in 1948, and experimentally confirmed in 1997 with high precision. Here is the setup. Take two perfectly flat, perfectly conducting metal plates. Place them extremely close together, a fraction of a micrometer apart, in a vacuum. In that vacuum, no air, no gas, no matter of any kind. According to quantum field theory, the vacuum is not actually empty. It seethes with virtual particles, pairs of particles and antiparticles flickering in and out of existence so rapidly that they are never directly observed, but their collective effect produces measurable pressure. Crucially, the energy of these quantum fluctuations depends on the wavelengths of virtual photons that can fit in a given space. Between the two plates, only certain wavelengths fit. Outside the plates, all wavelengths are present. This creates a pressure imbalance. The plates are pushed together by the outside vacuum fluctuations, which are more energetic than the inside ones, and the energy between the plates is measured relative to the outside, genuinely, demonstrably negative. The Casimir effect is real. Negative energy density is a feature of quantum field theory, not a theoretical fantasy. The bad news, and here the track drops again, is that the amount of negative energy available via the Casimir effect or any known quantum mechanism is extraordinarily small. The negative energy density needed to stabilize a traversable wormhole large enough for a human to pass through, by Thorne's own calculations, is stupendously enormous. For a wormhole with a throat radius of 1 meter, you would need a negative energy density on the order of the energy of a stellar mass squeezed into a region far smaller than an atomic nucleus, but negative. This is not just beyond current technology. It is, by many physicists' reckoning, beyond what the universe permits at macroscopic scales, even in principle. Stephen Hawking tackled this problem head-on with what he called the chronology protection conjecture. Hawking argued that the laws of physics, particularly quantum mechanics, conspire to prevent the formation of traversable wormholes, or any other configuration that would allow time travel, which traversable wormholes technically permit. He could not prove this rigorously, but the arguments were persuasive. The universe, Hawking suggested, does not allow you to rewire its history. And yet, there is a level of the physics where things get stranger still, where the story takes a turn so unexpected that even the physicists who discovered it spent years processing what it meant. This turn arrived in 2013 in a paper by two of the greatest theoretical physicists alive, Juan Maldacena at the Institute for Advanced Study in Princeton and Leonard Susskind at Stanford. The paper bore the deliberately cryptic title Cool Horizons for Entangled Black Holes. What it proposed has become known in physics shorthand as ER equals EPR. Let us unpack that. ER is Einstein-Rosen, the wormhole bridge. EPR is Einstein-Podolsky-Rosen, the famous 1935 paper in which Einstein, Boris Podolsky, and Nathan Rosen described the phenomenon we now call quantum entanglement, the spooky action at a distance that Einstein famously despised. In a quantum entangled pair, two particles share a quantum state such that measuring one instantly fixes the state of the other, regardless of the distance between them. Einstein thought this was proof that quantum mechanics was incomplete, that there must be hidden variables doing the work. Bell's theorem in 1964 showed Einstein was wrong, and decades of experiments have confirmed that entanglement is real and irreducible. Two particles really can be correlated across arbitrary distances in a way that has no classical explanation. Maldacena and Suskind's conjecture is this: quantum entanglement between two particles or two systems is not just a correlation. It is a wormhole. It is an Einstein-Rosen bridge connecting them through spacetime. Every entangled pair in the universe is connected by a microscopic wormhole through the fabric of spacetime. Every time you create quantum entanglement, and it happens naturally in particle interactions all around you constantly, you are creating topology. You are stitching space-time together with threads of connection that do not exist in ordinary flat geometry. The quantum foam that Wheeler hypothesized at the Planck scale, the seething, bubbling topology of space-time at distances of 10 to the negative 35 meters, where quantum gravity effects dominate, may be nothing other than a vast, churning network of Planck-scale wormholes connecting every part of the universe to every other part. This is not fringe speculation. This is taken seriously enough that it has generated hundreds of follow-up papers. The implications are staggering. If ER equals EPR is correct, then wormholes are not exotic anomalies requiring stupendous quantities of exotic matter to create artificially. They are the fundamental fabric of spacetime. They are what spacetime is made of, at the deepest level. We are not trying to build something unnatural. We are trying to scale up something that already exists everywhere, at every moment, in every cubic centimetre of space. But that does not make it easy. Scaling quantum-scale wormholes to macroscopic, traversable wormholes remains an unsolved problem of the first order. And there is a further twist, one that sends the roller coaster into a stomach-dropping plunge. Even in the ER equals EPR framework, The wormhole connection between entangled particles is non-traversable. You cannot send a signal or a particle through it. The correlations exist, but they cannot be used to communicate, because any attempt to do so would violate the no communication theorem of quantum mechanics, the principle that says quantum entanglement cannot transmit information faster than light. The wormholes are there. They connect. But they are locked. The door exists, but it has no handle on the inside. In 2019, a team at Google, in collaboration with theoretical physicists, including Maldacena, produced what they described as a quantum simulation of a traversable wormhole on a quantum computer. They encoded a simple quantum system that behaved mathematically like a two-sided wormhole, and showed that information inserted on one side emerged on the other. The experiment generated enormous excitement and equally enormous controversy. Many physicists pointed out that the quantum system used was so small and so idealized that calling it a wormhole simulation was more metaphorical than physical. The system was solving equations that have wormhole-like properties without actually curving spacetime in any way. The debate continues, but the fact that serious physicists are running experiments and calling them wormhole simulations tells you something important about how the field has changed. Now let us do what we came here to do. Let us forget, for a moment, the engineering problem of how you would build or find a traversable wormhole. Let us assume you have one. Let us assume it is there, hanging in space, large enough to walk through, stabilized by whatever exotic matter or quantum configuration is required. Let us take the equations seriously and ask, what do you actually see? What does the visual experience of approaching and falling through a wormhole actually look like according to an accurate ray tracing simulation of general relativity? The first thing that hits you, long before you are anywhere near the throat, is the lensing. Gravitational lensing. Light does not travel in straight lines near massive objects or extreme curvature. It follows geodesics, the shortest paths through curved spacetime, which are curved paths in our ordinary three-dimensional intuition. Near a wormhole, the spacetime curvature is not the crushing one-directional collapse of a black hole. It is more like a funnel connecting two funnels, a curvature that bends space both inward and outward in a way that produces extraordinary optical effects. Imagine you are approaching the wormhole from a great distance. To begin with, it looks invisible. There is no glowing portal, no shimmering gate, no obvious visual marker. The wormhole itself emits no light. What you see instead is a distortion of the background. The stars and galaxies behind the wormhole appear displaced. Light from objects that are actually behind the wormhole and to the side is being bent around the throat, redirected toward your eyes. Stars that should be hidden by the wormhole's position in space are visible to you, shifted from their true positions, ghosted and duplicated. If you did not know a wormhole was there, you would think you were looking at an unremarkable patch of sky with some oddly positioned stars. If you look very carefully, you would notice a subtle distortion, a slight visual warping, as if something were pressing on a fabric of the image in front of you. As you get closer, the effect strengthens dramatically. The wormhole begins to reveal its true shape. And here is the first visual surprise. A wormhole does not look like a hole. It looks like a sphere, a perfectly round, dark sphere floating in space, but dark in a very specific way. It is not the absolute darkness of a black hole event horizon from which no light ever escapes. The darkness at the wormhole's throat is inhabited darkness. Through it, if you look carefully, you can see the other side. Light from whatever is on the other end of the wormhole. Another region of space, another galaxy, another universe, is travelling through the throat and arriving at your eyes. What you see through the throat is a circular window into somewhere else. At moderate distances, that window looks like a dim, distorted fisheye view of another sky. The image is severely compressed by the extreme lensing at the throat. An entire hemisphere of the other side, potentially billions of light-years of space, is compressed into that circle. So everything you see through it appears miniaturized, curved, alien. If the other end of the wormhole opens onto a region of space with a different stellar density, the window will glow with the faint, compressed light of those distant stars. If it opens near a bright source, a galaxy, a nebula, another star, the window will be correspondingly brighter. The visual appearance of the far side, as seen through the throat, depends entirely on where the other mouth of the wormhole is located. Meanwhile, the stars around you are doing something extraordinary. As you approach closer, the lensing ring around the wormhole throat becomes visible. Light from stars in your own sky is being bent so severely around the throat that it forms arcs, curved streaks of stellar light curving around the sphere of the wormhole like brush strokes around a canvas. At a critical distance, related to the photon sphere of the wormhole, the radius at which light can orbit it, these arcs close into complete rings. This is the Einstein ring, the most spectacular demonstration of gravitational lensing possible. Stars directly behind the wormhole appear as perfect circles of light surrounding the dark sphere. Stars that are offset from directly behind appear as arcs, longer and more distorted the closer their line of sight comes to the throat. If the wormhole is threaded with any light-emitting material, dust, gas, plasma swept in from the surrounding space, these structures would glow as they spiral in, forming an accretion ring like the glowing disk you have seen in images of Messier 87, or in the simulations from Interstellar. Kip Thorne worked directly with visual effects company Double Negative on the wormhole and black hole visualizations for Interstellar, and the resulting simulations were so scientifically accurate that they generated 2 peer-reviewed papers. Thorne insisted on using the real equations. The results surprised even him. The accretion disk on the simulated black hole appeared above and below a disk simultaneously, because light from the far side was being bent over the top and under the bottom of the disk toward the camera. Nobody had predicted that visual effect before the simulation produced it. The equations knew something the physicists had not quite worked out in their heads. For our traversable wormhole, there is no event horizon, no point of no return before the throat. This is one of the key differences between a wormhole and a black hole. A black hole has a region, the event horizon, from which escape is genuinely impossible, where the escape velocity exceeds the speed of light. A traversable wormhole has no event horizon. You can turn around at any point before the throat. You can reverse your velocity, fire your engines, and retreat to where you came from. The wormhole's gravity pulls you in just as ordinary gravity pulls objects together, but it does not trap you, not before the throat at least. This means that as you approach, there is a long period of choice. You are falling, but you are not committed. The visual experience during this approach is one of the most beautiful things physics permits. Stars around the wormhole are being stretched into arcs and rings. The view through the throat is expanding as you get closer, occupying more and more of your visual field ahead. The view behind you, your origin point in ordinary space, is beginning to contract, compressed by the lensing, as if your home sky were slowly being gathered into a circle behind you. You are between two worlds, two bubbles of light, the familiar sky shrinking behind and the alien window growing ahead. At a certain point, both views occupy roughly equal parts of your visual field. A full hemisphere ahead showing the other side. A full hemisphere behind showing your own universe. The two separated by the lensing ring of bent starlight. The tidal forces at this point for a sufficiently large wormhole are gentle. This is the crucial engineering requirement that Morris and Thorne specified. For a wormhole with a throat radius of about 1 kilometre or larger, the tidal forces, the difference in gravitational acceleration between your head and your feet, would be small enough for a human body to survive. For smaller wormholes, tidal forces grow as the inverse cube of the throat radius, becoming lethal very quickly. The difference between a survivable wormhole and a spaghettifying one is entirely a function of scale, large enough to walk through gently, small enough to tear you apart before you even reach the throat. This is not a small engineering constraint. The negative energy requirements scale with wormhole size in a direction that makes larger wormholes even more exotic matter-hungry. There is no easy regime here. But in our simulation, our imagined fall, the wormhole is large enough, and the tidal forces are survivable, so you continue falling. And now you cross the threshold. What happens at the moment of entry is something that no human intuition is equipped for, something that requires the simulation to actually make concrete. As you cross the throat of the wormhole, the geometry of space-time around you flips. In ordinary space, if you look forward, you see one hemisphere of the universe, and if you look backward, you see the opposite hemisphere. At the throat, both hemispheres are visible simultaneously, but distributed in a topologically impossible way. Looking forward, you see the other side. Looking backward, you see your home universe. But looking to your left or right, or up or down, looking perpendicular to your direction of travel, you see a ring of light, the lensing ring containing compressed images of stars from both sides simultaneously. Your visual field has become topologically non-trivial. You are seeing two separate regions of space-time at once. The moment you cross the throat, the exact mathematical throat, the surface where the area of space-time cross-sections is, at its minimum, a remarkable visual transition occurs. The image of the other side, which was in front of you, inverts. Specifically, the sky inverts, the way a fisheye lens inverts when you pass through its focal point. Objects that were appearing at the center of the forward image appear to expand outward. Objects at the edge appear to move inward. The topology of the image flips, like turning a sphere inside out. And simultaneously, what you see when you look backward is now not your home universe, but the wormhole throat receding away from you. And beyond it, as if through a window, the sky you came from. Your home universe is now behind you, receding, visible through the shrinking circle of the throat. In a properly rendered simulation, which researchers at the University of Tübingen produced in a series of papers, visualizing geodesics in traversable wormhole spacetimes. This transition is a smooth, continuous flip of the visual field. There is no discontinuity, no moment where things simply jump from one configuration to another. The topology changes, but differentially. Every photon that reaches your eyes takes a slightly different path than it did a moment ago, and the combined effect is this smooth, sweeping visual inversion. And now you are through. You are in the other side. The throat is behind you, a receding circle containing a compressed view of where you came from. In front of you is the other sky. And here is the extraordinary thing about what you see. It looks almost normal. Once the transition is complete, once you are far enough from the throat that the lensing effects are small, the view ahead of you looks like ordinary space. Stars, galaxies, the same kind of vast emptiness you began your journey in. If the other side is a different region of our universe, far away, you will see a different pattern of constellations, because you are now looking at the sky from a completely different position, perhaps billions of light years from your starting point. If the other side opens into a genuinely different space-time, another universe, in the theoretical sense of a causally disconnected region, the sky may look dramatically different. Different density of stars, different abundance of galaxies, possibly even different fundamental constants if we take the multiverse scenarios of string theory seriously. The light you see on the other side is also shifted. This is a crucial and often overlooked point. The energy of photons passing through a wormhole depends on the difference in gravitational potential between the two mouths. If one mouth of the wormhole is deeper in a gravitational well than the other, which would be the case if one end were near a massive object, light travelling from the shallower end to the deeper end would be blue-shifted, and light travelling the other direction would be red-shifted. This is exactly the same as gravitational redshift between different altitudes in ordinary gravity. For a wormhole where both mouths are in similar gravitational environments, out in the relative flatness of intergalactic space, the shift would be small and perhaps imperceptible. But if someone had moved one mouth of the wormhole to orbit close to a massive object, the color of the sky through the throat would be visibly different. Astronomers have thought about whether this color difference could serve as an observational signature, a way to detect wormholes if they exist in nature. Which brings us to one of the most electrifying open questions in all of modern physics. Do natural wormholes exist? Not the Planck-scale quantum foam wormholes that may thread space-time everywhere, but large, stable, observable wormholes. The honest answer is that we do not know. General relativity permits them. The conditions under which they might naturally form remain unclear. Black holes are the natural product of gravitational collapse. Stars die, collapse, and leave black holes. There is no obvious natural mechanism that produces large, stable, traversable wormholes without some form of exotic matter to hold them open. But there was also no obvious natural mechanism for producing the universe itself. And here we are. One speculative but serious scientific proposal suggests that the supermassive black holes at the centers of galaxies might be wormhole mouths. Sagittarius A star, the 4 million solar mass black hole at the center of our own Milky Way, whose shadow was imaged by the Event Horizon Telescope collaboration in 2022, behaves from the outside exactly as general relativity predicts for a black hole. But the interior of a black hole is causally disconnected from us. We cannot look inside it. We cannot rule out that what we are calling a black hole is in fact a wormhole whose other mouth opens somewhere else. The observational signatures would be subtly different, and several papers have proposed observational tests. None have yet produced a definitive result. There is also the matter of wormhole stability under perturbations. A traversable wormhole held open by exotic matter would be sensitive to any perturbation of that exotic matter distribution. Drop a rock into the throat and the exotic matter configuration is disturbed. The negative energy density shifts, the throat begins to collapse. How quickly depends on the details. For some configurations, the throat would collapse catastrophically fast, faster than light, sealing the wormhole in a time too short for the rock to pass through. For others, feedback mechanisms might stabilize it. This is an active area of research, and the answers are not yet in. What we can say is that passively stable traversable wormholes, ones that stay open without active maintenance by some external system continuously resupplying the exotic matter, are extremely difficult to construct theoretically. This is one of the reasons physicists take Hawking's chronology protection conjecture seriously, even without a proof. The universe seems to arrange itself so that every mechanism for maintaining a traversable wormhole introduces instabilities that ultimately prevent it from functioning. And yet the mathematics does not close the door. It does not say impossible. It says, here are the conditions under which this would work, and here is why those conditions are difficult to satisfy. Mathematics, unlike nature, has no preference for what is easy. It simply describes what is consistent and what is not. Let us pull back now and look at what an accurate three-dimensional simulation actually produces when you render the wormhole experience in full, with a ray tracer that properly accounts for all the geodesics. The team at the University of Tübingen, led by Thomas Müller and Ute Kraus, produced exactly this kind of visualization and made it publicly available. What their simulation shows, step by step, is this. At a distance of about 10 throat radii, the wormhole appears as a small dark sphere with a distinct brightness ring around it, brighter than the surrounding sky because of the lensed light from both sides converging there. As you approach and the angular size of the throat grows, the brightness ring transforms from a single ring to a series of nested rings, each one containing a compressed image of the full sky from one side, nested inside an image of the full sky from the other side. The number of these nested rings grows as you approach because increasingly tightly wound photon paths contribute to the image. In the limit, as you get very close to the throat, the nested ring structure becomes infinitely detailed. Each ring contains a full sky image. Each of those images contains a ring. Each of those rings contains an image. like a fractal of spacetime topology. Inside the throat itself, during the fraction of a second or several hours, depending on the throat length, that you are traversing the connection, the visual field is extraordinary. You are in a tube of space-time curvature, but unlike a physical tunnel, the tube has no walls. There is nothing to your sides except the lensed images of both universes, wrapped around you in the lens geometry. Looking toward either end, you see one sky. Looking perpendicular to your direction of travel, you see the lensing ring, light from both skies, mixed and bent, creating a visual ring that encircles you completely. You are inside the lens. After emerging on the other side and moving away from the throat, the process reverses. The throat shrinks behind you. The circle through which you can see home gets smaller. The lensing rings contract, and eventually you are left with a small dark sphere receding behind you, surrounded by its rings, containing within it a compressed view of everything you left behind. And ahead of you, the new sky. Ordinary space. Whatever the universe looks like from this new vantage point. Now, what does this mean? Not for the physics of wormholes as a transportation technology which remains firmly in the category of speculative future engineering at best, but for what it tells us about spacetime itself. The fact that Einstein's equations, without modification, without additional assumptions, without any physics beyond the general theory of relativity, allow for geometries that connect distant points, allow for the topology of spacetime to be non-trivial, allow for shortcuts that violate our intuitions about distance while perfectly respecting the laws of physics, tells us something profound. Distance in general relativity is not a fixed property. It is a consequence of geometry, and geometry is not fixed either. It is dynamic. It responds to energy and matter. Spacetime is not a passive backdrop against which events unfold. It is an active physical object that can curve, vibrate, stretch, tear, and, possibly, fold back on itself. The wormhole is the most dramatic illustration of this dynamism. It is the cosmos saying your intuitions about what is near and what is far are local, contingent, approximate. At the level of fundamental geometry, nearness itself is mutable. What is the implication for the observable universe? We live inside spacetime. We cannot see its global topology. We can measure its local curvature. And we have, very precisely, with gravitational wave detectors and pulsar timing arrays and galaxy surveys. But whether the global topology of spacetime is simply connected, like a sphere with no handles or holes, or whether it has non-trivial topology, with wormhole-like connections stitching distant regions together, is not something current observations can determine. The universe could be filled with wormholes, and we might not know, because from the outside, a wormhole mouth that is not feeding on infalling matter and producing no distinctive signatures would be invisible. The event horizon. Telescope's image of Sagittarius A star is a shadow, not a directly imaged surface. What casts that shadow could in principle be a wormhole rather than a black hole, and certain signatures, specific patterns in the shadow's brightness ring, certain quasi-periodic oscillations in the infalling gas, could distinguish between the two. These discriminating observations are at the edge of current and near-future technology. There is also the matter of time, a traversable wormhole that connects 2 points in space can, with the right preparation, also connect 2 points in time. This is not a consequence of poetic license. It follows directly and inexorably from the mathematics. If you take one mouth of a wormhole and accelerate it to near-light speeds and then bring it back, special relativity tells you that the travelling mouth ages less than the stationary one. For an observer who knows the wormhole system, this creates a genuine time difference between the two mouths. You could enter one mouth and emerge from the other at a different time. How much of a time difference depends on how long and how fast the mouth was moved. The wormhole would function as a time machine. Not a time machine that lets you rewrite history arbitrarily. The paradoxes of closed time-like curves, which this generates, have been studied extensively. Roger Penrose, Kip Thorne, Stephen Hawking, and many others have explored the paradoxes and potential self-consistency requirements. The consensus is nuanced. There is no mathematical proof that time travel via wormhole is impossible in general relativity, but quantum effects, Hawking's chronology protection mechanism, likely prevent it. Specifically, a traversable wormhole that could be used for time travel would generate a feedback loop of quantum vacuum fluctuations, the same virtual particles of the Casimir effect, circulating through the wormhole and gaining energy with each circuit, building to a divergent energy density that would destroy the wormhole before it could be used for time travel. The universe apparently does have an opinion about this one. But this is speculation about machinery we do not have. Let us come back to what we actually know, what we have actually built and seen. We have detected gravitational waves, literally ripples in spacetime, with instruments sensitive enough to measure displacements smaller than 1/10,000th the diameter of a proton. We've imaged the shadows of supermassive black holes in 2 different galaxies. We have measured the expansion of the universe with enough precision to find a tantalizing inconsistency, the so-called Hubble tension, where measurements from the early universe and the late universe give slightly different values for the expansion rate, that may point to new physics beyond the standard cosmological model. We have the James Webb Space Telescope, staring at galaxies that formed 300 million years after the Big Bang, showing us that the early universe built massive, structured galaxies faster than our models predicted, forcing a revision of our understanding of how structure forms. Every one of these observations adds to the picture. None of them confirms wormholes. None of them rules them out. We are, as a civilization, in the position of beings who have derived the mathematics of ocean waves without ever having seen an ocean. We know the equations. We can predict the behavior. We can simulate the experience of surfing a wave in perfect detail. But we have never felt the water. The physicists who work on wormhole theory are not doing so because they expect to build one next decade. They are doing so because the wormhole is the purest test of our understanding of space-time. If you understand why and how a traversable wormhole would work, what it requires, what it looks like, what it does to photons passing through it, you understand general relativity at a depth that cannot be reached through textbooks alone. The visualizations produced by Müller and Krauss, by the Interstellar team, by researchers at Goddard and Caltech and Tübingen, are not just spectacular images. They are physical experiments run in the laboratory of mathematics, probing the structure of Einstein's theory in the extreme regime where gravity does things that no human intuition anticipates. And what those experiments reveal again and again is a theory of breathtaking consistency and creativity. A theory that contains, within a few elegant equations, universes full of wonders that were never explicitly put there. Einstein did not put wormholes in his equations. He put in 10 coupled nonlinear partial differential equations describing how curvature relates to energy and momentum. The wormholes were already there, hiding in the solutions, waiting to be found. Black holes were already there. Gravitational waves were already there. The Big Bang was already there. The possible existence of a multiverse connected by tunnels in space-time geometry was already there. All of it waiting. This is the thing that should make your skin go cold with awe, the thing that the roller coaster of physics deposits you at after all its drops and climbs. We discovered wormholes in an equation, not in space, in mathematics. And the question of whether they are out there in the universe, whether some civilization somewhere has figured out the exotic matter problem, whether the dark sphere we would see through our best telescope at some point in the future is not a black hole but a door, that question is still open. It has not been answered. It cannot be answered yet with the instruments we have. It is the most important open address in all of physics. You want to know what you would actually see falling through a wormhole. You would see the light of 2 universes at once, bent into rings around a sphere that is the throat of the connection. You would see the sky invert as you cross the threshold. A smooth, continuous topological flip of everything around you. You would see your home sky compress into a circle behind you, and a new sky expand to fill your view ahead. You would experience no jolt, no discontinuity, no special sensation at the moment of crossing, if the wormhole is large and the exotic matter is distributed smoothly, because nothing in the laws of physics privileges the throat as a special location for a local observer. The curvature would be the same on both sides of the throat, and you would cross it like crossing an invisible line on the Earth's surface at the equator, with the enormous difference that every photon in your visual field would be traversing a bridge between 2 separate regions of space-time. And the stars you see ahead of you would be stars that no human being in your home universe has ever been able to see, except perhaps through a telescope on the other side, looking back. And there is one final thought that the physics offers, the last quiet note at the end of this cascade. If ER equals EPR is correct, if wormholes and entanglement are the same thing, then every pair of entangled particles in the universe is already connected. Every electron that has ever interacted with another electron and become entangled, every photon pair produced in spontaneous parametric down conversion in a laser laboratory, every quark pair in every proton in your body that is in a correlated quantum state with some other particle. All of them are connected by a microscopic wormhole. The fabric of space-time is woven from entanglement. Space-time itself is a consequence of quantum information. And you, made of atoms, made of particles, embedded in a quantum web of correlations that stretches across the cosmos, are already part of a network of connections that makes the wormhole not an exotic addition to the universe, but a revelation of its deepest structure. The universe is not a collection of separate objects floating in empty space. It is a single, connected, topologically complex structure. And the connections are not just metaphorical. They are geometric. They are physical. They are there, right now, at the smallest scales physics can probe, threading through the vacuum around you, stitching you to the stars. You do not need to fall through a wormhole to be connected to the cosmos. You already are. The wormhole just makes the connection visible.